Welcome to part 2 of case study ex4, where we apply other key operators in Project Reactor classes. This part of the case study will show how we apply various Project Reactor flux operators like range, flat map, and subscribe to create, reduce, multiply, and display big fraction objects asynchronously. It also shows how to use mono operators like from callable, map, flat map many, and subscribe on. In addition, we show how to implement a generic blocking subscriber that takes up for the fact that the Project Reactor Flux class lacks a blocking subscriber operator natively. As always, you can follow along with the source code if you take a look at the link at the bottom of this slide. We're now back in the IntelliJ project for case study ex4. Let's go ahead and take a look at the ex4 file, which is the main entry point into the program. As you can see earlier in part 1 of this lesson, we talked about the test fraction multiplication stream method, and now we're going to turn our attention to test fraction multiplications blocking subscriber. This method will test big fraction multiplication using an asynchronous flux stream and a blocking subscriber implementation to make up for the fact that there is in fact no blocking subscribe method with Project Reactor's flux class. As usual, those methods will run in the background asynchronously using the async task barrier, and then the async task barrier's block call will block the main thread waiting for the computations to finish. Let's go ahead and take a look at the flux ex class. Here we see the test fraction multiplications blocking subscriber method. As usual, we start out by making a string buffer to keep track of the intermediate results. And the first thing we do is we write a string there indicating the thread ID where the asynchronous processing will begin. And of course, that will be the main thread, thread 1. We then go ahead and take a look at the next implementation, which is a local variable called blocking subscriber, which is an instantiation of a generic blocking subscriber class that we're going to use with the generic parameter for big fraction. We'll take a closer look at blocking subscriber in just a moment. But in a nutshell, what this does is it makes it possible to be able to wait for asynchronous computations to complete without requiring the enclosing method to return first. What we're going to do here, much like the normal subscribe operator, which is not blocking, is we're going to give it 3 parameters, which are lambda expressions. The first one is going to be used to handle the normal on next processing. In this case, you can see we just go ahead and append the result as a mixed string. We also have a way of handling errors. That's another lambda expression we provide here where we're going to log the error message and then display the string, all the strings. And then finally, we have the normal processing where we're going to go ahead and display things that occur when everything completes naturally. There's one more method that we pass in here that's different from what you might see in other subscribe operations, and that's going to be a long max value. And that's used to indicate that we want the publisher to send the data just as quickly as it possibly can. We'll come back and take a look at blocking subscriber in more detail here in a minute. But first, let's take a look at our main flux stream. In this case, we're going to use the range operator to iterate from 1 to 10 iterations. We're going to apply flat map, where we use the flat map concurrency idiom in order to be able to generate a random big fraction. We've done this many times before with our make big fraction factor method. Just a quick recap, that makes a random numerator that's very large and a random denominator that's much smaller, and then joins them together into a big fraction. We then use another interesting method from Mono that we haven't talked a lot about up to this point called flat map many. And what this is going to do is it's going to take in a mono, and then we're going to go ahead and forward the emissions into a returned flux. So we're going to basically go ahead and take this mono and then do a bunch of big fraction multiplications and reductions, and then return this as a flux. So what's going to come back from these calls will be a flux that will be combined together or merged with the flat map operation. Reduce and multiply fraction is just that same method we've used many times before, where we go ahead and take a big fraction that's passed as a parameter that's unreduced, we reduce it in a background scheduler, which in this case is the parallel scheduler, and then we take the reduced fraction and we multiply it by S big reduced fraction. So that's the large constant that we've been using to take some time for the computations of big fraction multiplication. So flat map many basically transforms the big fraction emitted by this mono into a publisher and then forwards the emissions into the return flux. And we use this in order to be able to then get back a flux that we can combine together. That flux that's emitted from this will then be handled by the subscribe call. And this particular subscribe call is going to take an instance of our blocking subscriber. Now we'll go and look at that in more detail in a second. But let me show you first what we're going to do at this point. Notice that this particular call will return right away and let the processing take place asynchronously in the parallel thread pool. But we don't want the program to exit, or at least this particular test function to exit. So what we're going to do is we're going to use a method defined on blocking subscriber called await. And what await's going to do is it's going to wait for all the asynchronous computations to complete, and then it'll return an empty mono to indicate to the async task barrier that all the processing is done. And we're just doing this to kind of emulate the blocking subscribe semantics that you would find with that method in the context of RxJava's observable class. There is no blocking subscribe method in Project Reactor for whatever reason, so we're going to emulate it here using a subscriber. So you could also see that when we do this call here, we're going to say, now we're going to wait for all the asynchronous computations to complete, and then we call the await call. That await call will not return until all the computations are done. So let's go have some fun, and we'll take a look at the implementation of blocking subscriber, which we can find over here. So here's the blocking subscriber utility class. As you can see, it's a generic class that's parameterized by type T, which in this case is big fraction, but could be whatever. And it handles blocking, which is otherwise not well supported by Project Reactor. So we implement the subscriber interface, and then we go ahead and provide some fields, and we then go ahead and provide some methods that are inherited from subscriber. The first field we have here is a countdown latch, which the program that calls this, the calling thread, will use this to wait for all the computations to be done. If you come down here, just to go to the bottom, you can see that this is what await does. Await will go ahead and call the await method on the countdown latch, waiting for it to be counted down to 0. And then when it's counted down to 0, we're going to go ahead and return s void m. And s void m, as you may recall, is just a mono of void that holds an empty mono. And we use that to tell the async task barrier that we're finished. So coming back over here, we have this countdown latch. We have a consumer called mConsumer that handles the normal processing with the onNext signal. We have the error consumer that handles the onError signal. And we have the complete consumer, and that handles the complete signal, as you might expect. And then the final field we have here is MN, which is a count of the strictly positive number of elements to request to the upstream publisher. And that could be whatever you want it to be. Here's the constructor. We pass in the consumer, the error consumer, and the complete consumer, and N. The constructor creates a countdown latch with a count of 1. We make the consumer, error consumer, and complete consumer use them to initialize the various fields, and then we set N to, we set the value of MN to N. Let's now go take a look at await. We've already looked at that. Now let's take a look at the other methods in the class. Here is onSubscribe. This is the method that gets called back by the publisher after we have subscribed. And what it does is it says, how many requests should I send? And we give it MN, which in our example is set to the max value of a long, which means send these things as fast as you want. But you can easily change that if you want to only send little chunks at a time in order to provide support for back pressure. Here's the onNext hook method. As you can see what onNext does, this gets called back when we normally get an event that's an onNext signal. And all it does is it simply accepts that into the consumer field. So it basically does whatever we pass into the constructor. OnError works much the same way. We go ahead and accept the throwable into the consumer, whatever it was designed to do in the constructor, and then we release the latch because we're done. And then the onComplete method goes ahead and runs the complete consumer, which we also passed in, and it then goes ahead and releases the latch by doing a countdown. So that's how we're basically going to be able to have this block and then get released when all the processing is finished. So this is essentially a good example that illustrates how to write a blocking subscriber. We have a generic blocking subscriber, so you can reuse that for whatever purposes you may have. You don't always need a blocking subscriber, but for things like testing, it can sometimes come in useful if you don't want to go to all the trouble to use the async task barrier. And this also demonstrates the use of the flat map many method, which can be used to convert monos into fluxes, which is exactly what we're doing here. So that's the end of this particular walkthrough of the test fraction multiplications blocking subscriber method. Hopefully you now have a better understanding of these more complicated capabilities that are defined by different classes in Project Reactor.